A wire of length L equal to 4 meter and cross sectional area equal to 1 millimeter square, carrying a current of 2 ampere. If each cubic meter of the material contains 10 to the power 29 free electrons, find the average time taken by an electron to cross the length of the wire. We have T equals to L by Vd, or L by Vd equal to J by Ne, or N into L by J, or N into L by J equals to I by A. So Ne L A by I. Now number density is given. Ten to the power 29, and E is 1.6 in 10 to the power minus 19. L is 4 into 10 to the power minus 6. L is 4 and A is 10 to the power minus 6, because A 1 millimeter square, divided by I equals to 2, because 2 ampere is current flowing. So 2 ampere equals to 3.2 into 10 to the power 29 into 10 to the power minus 25. 3.2 into 10 to the power 4 second equals to 8.9 hours. Next question. Calculate the electric field in a copper wire of cross-sectional area 2 millimeter square carrying a current of 1 ampere. The resistivity of copper 1.7 into 10 to the power minus 8 ohm meter. Here E equal to rho into J, or rho into I by A, given rho equal to 1.7 to 10 to the power minus 8 into I equal to 1 and A equal to 2 into 10 to the power minus 6. So we have 1.7 divided by 2 into 10 to the power minus 2 volt per meter, 0.85 into 10 to the power minus 2 volt per meter, or 8.3 into 10 to the power minus 3 volt per meter. Answer. A wire has a length of 2 meter and a resistance of 5 meter. Find the electric field existing inside the wire if it carries a current of 10 ampere. We have R equal to rho into L by A, so A equal to rho into L by R. Now J equal to I by A, so J by rho into L by R. Hence J equal to I R by rho into L. Hence E equal to I by, or now E equal to rho into J, so rho into IR by rho into L, rho cancel, so I into R by L, E equal to I into R by L, or equals to 10 into 5 by 2, 25 volt per meter. Answer. Temperature dependence of resistivity. The resistivity of a metallic conductor increases with increasing temperature, as rho f equal to rho I under bracket 1 plus alpha into delta t plus beta into delta t square, where delta t is the Tf minus Ti temperature difference, final temperature minus initial temperature. Rho f is the resistivity at temperature Tf, and rho I is the resistivity at temperature Ti. Alpha and beta are temperature coefficient of resistance. Ti initial temperature, Tf final temperature. If delta T is small, then rho F equal to rho I into 1 plus alpha into delta T. So with rise in temperature, resistivity will increase if alpha is positive, that is for metals, and will decrease if alpha is negative, that is for non-metals, because alpha is negative for non-metals. Now temperature coefficient of resistivity is given as alpha equal to rho F minus rho A by rho I into delta T equal to delta rho by rho I into delta T, or in general form we can write alpha equal to delta rho by rho into delta T. So this is the relation between resistivity, coefficient of resistivity and resistivity with temperature. Temperature dependence of resistance R. We have rho F equal to rho I into 1 plus alpha into delta T. Multiplying both sides of a equation with L by A, we get rho F into L by A equal to rho I into L by A into 1 plus alpha into delta T. This implies Rf equal to Ri into 1 plus alpha into delta T, where Rf is the resistance at temperature Tf and Ri is the resistance at temperature Ti, delta T Tf minus Ti, and alpha is the temperature coefficient, and alpha is the temperature coefficient of resistance, hence alpha equal to Rf minus Ri by delta T equal to delta R by R into delta T. Thus temperature coefficient of resistance and temperature coefficient of resistivity are same for a given material. The temperature coefficient of resistance and temperature coefficient of resistivity are same for a given material. Next, temperature coefficient of resistivity is defined as the change in resistivity per unit initial resistivity for unique change in temperature. Second, temperature coefficient of resistance is defined as the change in resistance per unit initial resistance per unit change in temperature. The resistance of an iron wire and a copper wire at 20 degrees Celsius are 3 ohm and 4.1 ohm respectively. At what temperature will the resistance be equal? Coefficient of resistance alpha iron for given 5.0 into 10 to the power minus 3 per Kelvin, and coefficient of resistance for copper is given R alpha Cu 4.0 into 10 to the power minus 3 per Kelvin. From the problem it is given RIFE. According to problem, RFFE is equal to the RFCU. Yeah. RFFE equal to RFCU. RF final resistance of iron is equal to the final resistance of copper for the same time interval. So this implies now RIFE into 1 plus alpha Fe into delta T, RICU equal to 1 plus alpha Cu delta T. This implies RIFE plus RIFE into alpha Fe into delta T, and RICU plus RICU alpha Cu into delta T. Now taking this one side and this one side, so RIF into alpha Fe minus RICU into alpha Cu into delta T equals to RICU minus RIFE. Hence delta T will be RICU minus RIFE divided by RIFE into alpha Fe minus RICU into alpha Cu. This implies Tf equals to Ti plus RICU minus RIFE divided by RIFE into alpha Fe. Ri Fe into alpha Fe minus Ri Cu into alpha Cu, and so we have putting the value, given value 20 degree plus 4.1 minus 3.9 divided by 3.1 into 5 into 10 to the power minus 3, 4.1 into 4 into 10 to the power minus 3, or 20 degree plus 0.2 divided by 19.5 minus 16.4 into 10 to the power minus 3, or 20 plus 0.2 by 3.1 into 10 to the power 3, or 20 plus 2 by 31 into 1000, and 20,000 by 31 plus 20 equal to 64.5 plus 20, or 84.5 degrees Celsius answer. Next, mobility mu. It is defined as the magnitude of drift velocity per unit electric field. It is defined as the magnitude of drift velocity per unit electric field. So mu equals to, that is mu equals to mode of Vd by E, or mu equals to Vd by E, or equals to Vd equal to E tau by m into E, or E tau by m. So mu equal to E tau by m. SI unit of mu Vd by E, meter per second by volt per meter, or meter square per second per volt, or meter per second by Newton per coulomb, or coulomb meter per second by Newton. Again mu equal to E tau by m, the coulomb per second by kg, or coulomb per second per kg. So these are the units of SI unit will be this, meter per second by Newton per coulomb. Now limitation of Ohm's law. Ohmic conductor flow Ohm's law, that is V proportional to I, or Vi graph is a straight line. Example, metallic conductor. Non-ohmic conductor do not flow Ohm's law, that is V is not proportional to I for this conductor. Vi's curve is not a straight line. For example, vacuum tube, semiconductor, diode, liquid electrode, tetrode, thermistor, etc. In this type of material, electron is not directly proportional to voltage. Current is not directly proportional to voltage. For here example, this is ohmic conductor. For metallic conductors are ohmic conductors, so I is proportional to V, and graph is a straight line between I or V, or V or I. Now for electrolytes, graph is like this. This is not a straight line, so it is a non-ohmic non-ohmic conductor. Is also conductor but non-ohmic. And here it is a semiconductor light emitting diode, non-ohmic. The variation of current and voltage is shown here. In tetrode, non-ohmic because current is always constant. In diode, such type of Vi characteristics, and in thermistor it is also such type of graph. So these are non-ohmic conductor. Yeah, non-ohmic material, don't say conductor, non-ohmic material you can say. Now resistor or resistance. There are two types of resistance. Wire bound resistor. It is also one we can also say resistance, but it will be very it is true to call it as a resistor. Wire bound resistor made by binding the wires of Ly, manganese, constantine, nichrome, etc. are used to make resistor by bounding them. And carbon resistors, cylindrical and 4 or 3 circular ring strips on them. These are carbon resistors. Now it is carbon resistor. There are circular strips on them, and binding circular resistance, and these colored strips represent the resistance and their percentage accuracy.